Hi, you guys. All right, I have so many things that my plan is to just talk even faster than yesterday. So, what are we here for? Well, we're here because what we want to do is understand what does deep tech mean and what's possible. And when we talk about deep tech, I think it's important to sort of separate it from what are we not talking about, which doesn't really have a name, so I made one up. And I call it shallow tech. And shallow tech is all this other dumb shit that people think of as technology, but is really just software. So what we want to do is look at what is the cool shit that we can do in the world is not exclusively software, because we think we live in a world full of technology, but we really just live in a world full of software. And there are a lot of things that you can't do with software, and some of those are things that we should do. So I want to pick that apart a little bit. I'm going to give you some examples. Years ago, I worked on this project. It's called MakerBot, and it was the first consumer 3D printer that you could sort of have at home. And before MakerBot, no one had ever seen a 3D printer. It was like an exotic machine that only existed in labs. And what we were able to do is make something that kids could have. You know, my daughter was 5 or 6 years old, and we had one of these on the table at our house, and she would print high-heeled shoes for herself. Kids grow up with these things. This is how they think of making things. And what's different about 3D printers is they're programmable. So if you look at how we make stuff in the world, in factory automation, we're often you make a machine that makes one thing and then amortize the cost of it over thousands of units. But then when you want to make version 2, you throw it out and make a new machine. And that's not how we want to make things in the future. We imagine that we're going to be able to make factories of 3D printers where you can just draw something in Minecraft and click print and it's going to go make it for you, right? Because that's how kids think. And that's how our engineers are being trained. They're growing up with these programmable machines that never have to make the same thing twice. And that hasn't worked out very well. You know, we don't have these kinds of factories working. The things you buy don't come from 3D printers. And a lot of the reason for that is that, well, there's two big reasons. One, they're slow, because they're like 1-pixel printers, right? They put down a pixel at a time. And that's too slow. But the second big reason is that the input materials have to be very high quality, and they're very expensive. And at the end of the day, you're competing with injection molding, which would be the cheapest possible way in the world of making anything. Injection molding in China. So if we want to automate our factories and make them programmable, reshore them to Europe and the US and the places that are closer to the actual customer, we have to be able to make these things cost effective. Well, I met these guys who figured out how to adapt the powder bed style of 3D printers. Those are used for metal. And that's kind of the one thing that has worked in manufacturing, because metal parts are more high value, right? And the printers are faster because they put down a layer of metal powder and then they bind it together. And they print a layer at a time instead of a pixel at a time. But these guys figured out how to adapt the metal style of printer to print with used coffee grounds from Starbucks. And what's interesting about that is that now the input material costs less than zero. They get paid to haul this stuff away from Starbucks. They throw it in the printer binds it together, and they're printing all kinds of durable goods. They print these coffee mugs, they powder coat them or metalize them. You can't tell the products are made of coffee. They're making sinks this way. They're making, all kinds of, durable goods, light fixtures. They just metalize them. You can't tell it's made of coffee. And it costs less than making the stuff in Asia. And it's fully automated. Right? And of course, along the way, you're sequestering carbon, you're keeping biomass out of landfills. There's really nothing not to like about this. I mean, they're also doing it with seaweed and sawdust. They figured out how to print with biomass. And I think these kinds of things are important because they are possible and they're better. And when we're talking about deep tech, a lot of times what we're talking about is really modern industrials. Like, how do we go back and look at the industries that humans have built and grown over the last century or two, take the new technology superpowers that we've got, and reinvent them so that they can be 10 times better, 100 times better, 1,000 times better, right? That's what's possible in a lot of cases. Most industries are busy trying to make themselves 1 or 2% better. But if you can get a new technology that allows you to reinvent how you do something, sometimes you can get those 10x multipliers. And that's really where the potential is to solve a lot of the big problems we have in the world. A lot of people don't realize this. A cargo ship spits out really nasty smoke. You don't see that smoke because it has a second gas tank where it burns refined fuel like your car. So when it's in view of people, they normally don't do this. They burn the clean stuff, or it's not clean, it's just cleaner. And then when it gets out of sight, they switch to the nasty stuff, right? But why do that at all? We could make cargo ships that sail themselves. It's like easier than self-driving cars. The sailing's been working for, 400 or 500 years, crossing oceans with sails. We know that works. Why would we do that? Like, these things are unquestionably better. The technology's not that hard. We know we could do it. This is an industry that's probably twice the emissions of air travel, cargo. We build almost everything in the world out of cement. It's the single most used construction material in the world. I think it's the single most used material in the world. It is also the material most responsible for carbon emissions. And that's because cement, there's a couple parts to that. One is you're throwing a lot of coal or gas or something to fire up a furnace to heat it up. So a lot of emissions there. But the other reason, you could maybe get rid of that by electrifying the furnace. But the truth is, most of the emissions comes from the chemical process of making the cement. And that you can't get rid of. And this is an interesting one because the cement only lasts for like 50 or 100 years. All of it cracks. Water seeps into the cracks, kind of destroys it from the inside out, and it crumbles, which is frustrating. We try to partially ameliorate that by putting steel rebar in it, so we reinforce the cement with steel. Well, it still crumbles. But look at this. You recognize that? It's called the Pantheon. It's a building the Romans built 2,000 years ago in a seismic zone out of cement with no steel reinforcement. Right? Yet it stands. And somehow, the Romans were able to build these things, and then we just sort of forgot how to make cement the way they did. Their cement lasts 2,000 years, ours lasts 50. What's going on? Well, it turns out the Roman cement has extra lime trapped in it. And so what happens is when it cracks, water seeps into the crack, and then activates that lime, fills the crack. It's kind of amazing. This just gets stronger over time. But nobody's been able to figure out how they did that. I found a team at MIT that just figured it out. And so now we know how to make cement the way the Romans did. And it's unequivocally better. It doesn't cost more. You can do it in any cement factory. You can use less of it, use less steel. And the kicker, 20% less CO2 out of the box. Like, we can do better on these things now. Years ago, many years ago in my childhood, I grew up with this thing. It's like the first home computer that you could have in the world. But I grew up in Alaska, so nobody for like 1,000 miles in any direction had a computer. And so I had to learn everything the hard way. And it was pretty useless. In those days, computers were super slow. The spreadsheet hadn't been invented yet, so people were pretty conflicted about whether it was actually a waste of time or not. And I thought, someday it'll get faster, someday it'll have more memory, and someday it'll be useful. And really nobody believed me. In fact, I had this thing and I also had a skateboard. And most people weren't sure which was a bigger waste of time. But revenge of the nerds, I was right. Eventually computers got fast. This is the one I was fantasizing about. It's called a Cray XMP, 400 megaflops. Just imagine what you could do with all that computational ability. Well, now every one of you is hauling around something like 2 teraflops in your pocket. It's insane in a way. We're no longer computationally constrained. We're imagination constrained. We don't even know what to do with all this computational ability. This is a totally fake slide that I made up. But you guys have all spent plenty of time in Excel, making a spreadsheet, spitting out charts and graphs like this. This is not what computers are for, okay? Nothing interesting will ever be done this way again. You can just take Excel, drag it into the trash, empty the trash, right? Because this is what I call small data, right? Now, we use these giant supercomputers, and mine has 5,000 cores and a lot of blinking blue lights, and it's super cool, but there is no reason you need one of these. You can just rent them by the minute from Amazon. Anybody can get access to a massive amount of computational ability, right? But what we use them for is to make these kinds of computational models. I think it's really important to understand that's what we're talking about. We're making computational models. SimCity is a computational model of a little city. And you get to try destroying it in different ways. It might be a really wise thing for the people running actual cities to spend some time in SimCity first, right? Because models are how we test our ideas, right? My daughter grew up making models. She would just, these driving little cars around her fake little city. In her mind, she's creating a model in her brain. All of you have done this. You all have a model in your mind that you created over your life. You can close your eyes and picture your bedroom. You can close your eyes and picture how to get out of this room. Your mind is creating models, but it's only making one. And the cool thing about the computers is they can make a lot of models, and they can run a lot of simulations. So when we talk about artificial intelligence, I think it's a little bit of an exaggeration. What we're really talking about is we've created big models, right? You've been using Google Maps for 15 years every day. It's a model of the streets in the world. When you ask it, how do I get home? It says, here's a simulation. Right? Follow the blue line. But it also gives you a couple of gray lines. Oh, here's other options. Right? It's showing you your possible futures. And you can choose from that which one you want to go for. We use this type of technology to make models of the spread of disease, infectious disease, largely in the developing world. So we collect data on climate, rainfall, the travel of humans, all the kinds of things that can affect the spread of a disease. In this case, we're modeling malaria. And what it allows us to do is see over years into the future how the disease will spread. So this is a model of Madagascar. And incidentally, if you go to Madagascar, you should probably go to the middle. That's kind of where the people still are. In the rainy season, malaria covers almost the entire island, but in the dry season, it'll go away almost entirely. And because we have these models, we can test our interventions thousands of times in software before we do it in the real world. This is not science fiction. We've been doing this for 15 years. We're advising 75 different countries on how to optimize deploying their vaccination resources. This is how we save millions of lives a year, right? In the first Ebola outbreak, 12,000 lives were lost. In the second Ebola outbreak, only 12 lives were lost, just a couple years later, right? In part because using computational models like this, we're able to optimize the ring vaccination campaign, optimize how we deploy those resources, contain the disease before it spread. That's what would have been possible with COVID. But we weren't paying attention, right? These technologies are new superpowers for humans to help us see what are our possible futures and choose the one that we think sounds the best. And I think you guys can all understand this. And probably in this audience, we have people who understand these technologies pretty well. But if you think about a picture in Instagram, that is a computational model. It's a data structure, right? A picture in Instagram is the same thing as a spreadsheet in Excel, right? In Excel, you got a cell with a number in it. In a spreadsheet, you got a pixel. The number is what color is this pixel. Same thing, right? Basically, everything works that way in computers, right? So what happens? Well, when you're going to run a filter in Instagram, that's another way of saying an algorithm, which is another way of saying a formula in a spreadsheet, right? It's the same thing, except that a formula in a spreadsheet is typically small enough that you could sort of read it and figure out, A2 plus B2 equals, right? But here, what's happening is I'm going to change the color of a pixel, and then I got to compute what happens to the 8 pixels around it. Well, shit, now I got to compute what happens to the 8 pixels around each of them, and I have this giant cascading exponential amount of computation. That's why it's hard. But computers love to do math. So we can do it. And that's how, and it's so fast now, you're not even waiting. It happens in real time. The progress bar, anybody remember progress? Gone. Like, we don't have that anymore. Computers are so fast. So the point is, when we use all these fancy terms, artificial intelligence, machine learning, transformers, neural nets, whatever, we're just trying to sound smart. You can totally understand this stuff. It's the same thing. Neural nets, basically the same thing. We just have the computer randomize a bunch of algorithms, test them all, throw out the ones that suck. That's it, right? So when you're talking about these machine learning algorithms, the difference is just that it's so much data no human could ever ingest it all. And the algorithms are so complicated and long that no human could ever understand one, right? But they're good at giving us better answers if we learn to wield these tools. So that's going to start to affect everything. And the reason I'm dragging you through all this in the deep tech context is that a lot of times people will say to me, well, you're trying to do these super technical things, isn't that hard? And I'm like, yeah, all the easy shit's been done. So yeah, we're going to go do the hard things now. But also, it's easier than it was. And it's easier than it was because what made software so powerful was the rapid iteration, the ability to just, for very low cost in time and effort, try a lot of experiments and A/B test your way to success. That's why software works so well. And it's not because it's software, it's because of the rapid iteration. Well, guess what? Now we can model almost everything in the world. If I'm building a hypersonic jet or a rocket or a Tesla or whatever, I design it in software, I test it in software, I crash it in software, and then I figure out which design is the best, and I go build one. Right? Iterating in hardware, yeah, that is hard and expensive and slow. But iterating in software, we can apply that to almost everything else in the world, and that's why we're making advancements in synthetic biology. That's why we're making advancements in physics for applying it to all these kinds of problems, right? And so we're at this moment in time when the toolkit we have to go do the hard stuff is helping us accelerate that. And it's exciting because now we get to go take on all these big problems and the things that we've been ignoring. So I think this is important. We are all made of stars. And I said this yesterday, but this is our sun. This is the star that we are made of. Like, all the energy that you need to survive, to exist, comes from that sun. And that includes the solar power, but it also includes the coal and the gas and even the photosynthesis that makes plants for everything you ever ate. Even if you don't eat plants, they feed the things that you do eat, right? And it even includes like the uranium in the ground, right? And we need to make enough energy to power you. And the average person on Earth gets as much energy as a single toaster running 24/7, right? That's all the energy you need to survive, to power your cooling and heating. It's the energy you need for transport, for your food, everything, one toaster. I like to make fun of Americans who get 8 bonus toasters, right? We get about 9 or 10 times as much energy as the average person on Earth. Europeans, in general, were kind of running at about 5 to 6 toasters until recently, and now they're down to like 4 to 5. Not because they want to, just because they can't get any more energy. But to get these averages, 3 billion people have to live on less than 1 toaster, right? And again, not because they want to, but because we haven't provided enough energy for them. So the true demand for energy in the world is 10x global energy production. And I don't think we're being honest with ourselves about that. It sounds unfathomable. It's the true demand for energy. How do you give every human on Earth the living standard that we get? Right? That maps to energy. And if you want to solve all these other problems, you kind of got to solve energy first. But here's the thing. 10x global energy production sounds insane, but we have done it before. In the last century, we 10x global energy production on this planet. Now, we did it by burning more coal, burning more oil, burning more gas. Probably we don't want to 10x using that stuff, right? We have learned our lesson. At some point, there's only so much shit you can put in the toilet before it doesn't flush anymore. That's what we're dealing with. So we want to 10x using what we call renewables, right? Let me show you a couple things. This is all of the metals mined in the world last year. Aluminum, copper. This gives you a visual sense, but check this out. They all pale in comparison to that one, right? We mine so much iron that those don't even register. But look at this one, this tiny little pile here, uranium. In that one pile, there's enough energy to power the entire planet, everyone, just from that amount of uranium we mine in 1 year. We could get rid of all the coal, all the oil, all the gas, everything, just with the energy we already mine from uranium. It's so energy dense that if you had a single can of uranium, the size of a soup can, you could power you and your family for your entire lives with just that one can, right? But it's radioactive and dangerous and messy, and we don't know what to do with the waste, so we've been saving it for our grandkids in these stockpiles. We invented a new type of nuclear reactor that's powered by nuclear waste. You literally take the waste left over from making bombs and put it in this thing. It enriches it and burns it. What a lot of people don't realize is today's reactors are only 0.7% efficient. 99.3% of the energy is still in the nuclear waste. These modern reactors can get the rest of that energy out, all right? This is a stockpile in the US in Kentucky. 700,000 metric tons of depleted uranium, saving it for our grandkids. Left over from making bombs, left over from making reactors, right? With this one stockpile, we could power the entire planet, including growth, for the next 1,000 years. We don't even need to mine uranium. Like, we have this miraculous energy source, but what happened is humans told ourselves the wrong story, right? We started to conflate nuclear reactors with nuclear bombs. We got mushroom clouds in our heads. We outlawed nuclear reactors before we understood them. And we are living with the consequences. If we had built nuclear reactors since the 80s, you never would have heard of global warming. That's what's possible. But we made the wrong choice, and now we're living with the consequences, and we have to course correct. That's one way we could do it, build a lot of nuclear reactors, and we should. There's another way that people are looking towards, which is fusion. Fusion is exciting because you don't even need to mine uranium, and you could potentially make a machine that emits more energy than it takes to operate it. Everything we do now, you just put fuel in, whatever the fuel is, you put it in and burn it until it's gone. But a fusion reactor, if we get it going properly, it can actually produce more energy than you put in. And we know this is possible because of the sun. The sun does that all day, every day. It's fusion. We're just trying to figure out how do you do it on Earth without, melting everything. And this used to be the kind of thing that was fantasy for scientists, but just in the last few years, we got the last breakthrough we needed to be able to do it. So there's no new science necessary to accomplish this, but there's a lot of hard engineering work, and it's going to take some time. And I don't think we should be sitting on our thumbs waiting. But if it works, maybe 10 years, 20 years from now, you'll be able to power you and your entire family for your entire lives off of one glass of seawater. That's what fusion can do. So look, I invited a couple of my favorite founders to come up here with me today. First one that's coming out is John Bucknell. He's the founder of Virtus Solis. And this is a company that has another way of solving energy in our lifetime. And I'm so excited to share this with you. It's one of my favorite things in the entire world. And so we're going to get John out here, and then he's going to show you what he's doing, and then we can take some questions about it after that. So thanks for listening. Yeah.